Right now, wherever you are, I want you to notice the tiny world around you. Maybe you're in a dim room, the only light coming from this screen. Maybe there's a soft lamp in the corner, or a window with night pressed up against the glass. You might be sitting at a desk, curled up in bed, or half lying on a couch that knows your exact shape by now. Listen for a moment. There might be the slow hum of a fan, the quiet buzz of electronics, the distant rush of a car outside, or almost nothing at all. Your body feels still. Your weight is pressed into a chair or a mattress. Your feet rest on the floor, or your head sinks into a pillow. You breathe in, you breathe out. The air on your skin is a certain temperature, a certain softness. It all feels calm and unmoving. Now imagine pausing here. Freeze this picture of your life. This room, these walls, this ceiling, this tiny island of light in the darkness. Think about that for a second. Everything in your senses is telling you that you are at rest, solid, grounded, going nowhere, but you are not still, not even close. Right now, you are riding on a spinning planet, which is looping around a star, and that whole system is gliding through the Milky Way. There's no wind in your face, no seatbelt sign, no gentle voice saying, "We know you have a choice of galaxies when you travel." And yet you're strapped to this star, whether you like it or not. Let me give you the clearest possible example. Take a slow breath and notice the weight of your hand resting on a mouse, a phone, or a blanket. That hand feels heavy in one direction, down. It feels like the most ordinary thing in the world. But that same hand, that same quiet weight, is being carried through the galaxy on a vast, invisible path. Your room is coming with you. The building around you, the street outside, the city lights, the clouds, the oceans, the entire planet. Every bit of it is riding along together, as if placed on a gigantic, unseen conveyor in space. There's no rattling, no shaking, because everything you know is on the same smooth ride. The motion hides inside the calm. Here's something that will make you smile. From your point of view, you're just watching a video. In this video, we're going to peel back that feeling of stillness and reveal the journey beneath it. I want you to hold both ideas in your mind at once. The quiet of your room and the fact that you, right now, are already drifting through the galaxy on a silent, enormous voyage. The only question is, what out there in the darkness is pulling us along? So let's lift that feeling of stillness one more layer. Not just Earth quietly circling the sun. Not just the sun sliding around the center of the Milky Way. The whole Milky Way itself. This vast river of hundreds of billions of stars is falling through the darkness towards something we can't even see clearly. Astronomers have given it a name that sounds almost poetic. The Great Attractor. A patch of sky in the direction of the constellation Norma, where galaxy after galaxy seems to lean, as if space there were a hidden valley, and everything nearby is slowly rolling down its slopes. Think about that for a second. Our entire galaxy is one of those rolling things. Here's something that will make you smile. You didn't sign up for this ride. You never saw a ticket counter. And yet, you are strapped to a star, inside a spiral galaxy, inside a larger cluster of galaxies, all drifting toward this invisible weight. There's no engine, no cables, no glowing arrow in the sky saying, This way. Just gravity, quietly doing what it always does. Let me give you the clearest possible example. Imagine you're sitting on a long train at night. The blinds are half closed. You can't see the locomotive at the front. Out the window, the landscape moves so slowly, you're not even sure if you're moving or if the world is. Trees slide by. A distant town light shifts position. You feel nothing in your seat. But over hours and hours, the view changes. On cosmic scales, you are that passenger, and the Milky Way is the train. From our point of view, the landscape is the leftover light of the Big Bang itself, the cosmic microwave background, glowing faintly from every direction. When astronomers measure it very carefully, they see a tiny tilt, a warm side and a cool side, like a breeze in that ancient light. That tilt tells us something astonishing. The Milky Way is moving at over 600 kilometers per second relative to this background, more than 2 million kilometers every hour. And yet you feel none of it. No wind, no sway, just the quiet of your room. Now imagine stacking all these motions together in your mind. Earth around the sun around the galaxy through an even larger structure, a kind of cosmic watershed called the Laniakea supercluster, where galaxies follow slow, graceful flow lines toward common basins. You are a tiny point in one of those flow lines, being carried along a hidden river of space-time. This is going to be a long, calm journey, and the Great Attractor is only the first bend in that river. Because when we look past it, through the glare of our own Milky Way and deeper into the darkness, we find hints of something even more massive tugging on us from farther away. The question is, what kind of structure could pull on entire galaxy clusters and still not be the end of the story? To really feel what that means, we need to come all the way back home for a moment. Back to your ceiling, right now, wherever you are, whether you're lying in bed, sitting at a desk, or sneaking this in on a couch somewhere. You're under a roof, under a ceiling, inside a little bubble of space that feels sealed off from everything else. I want you to actually look up, or at least picture it. The flat surface. Maybe a light fixture, a crack in the paint, a slow fan turning. The ceiling feels like the top of your world. It's the lid on your personal universe. Think about that for a second. Your brain is very good at treating that room as the whole story, as if nothing important is happening beyond those walls. Now imagine we start to zoom out, slowly. First, we pull back just enough to see the roof above you, the building, the street. Then the town, the lights, the thin grid of roads. Keep going. We rise through the damp air, past apartment windows and office towers, until the last street lamp is just a pin of light in a patchwork of dark. We push higher, through the clouds that glow faintly from city light, through the cold, thin shell of atmosphere that's only a few 100 kilometers thick. Here's something that will make you smile. For all the talk about outer space, the air blanket that keeps you alive is thinner compared to Earth than a coat of varnish on a classroom globe. Above that varnish, the blue fades. The sky stops being a ceiling and becomes a backdrop. The darkness turns real. No more scattered glow from billboards or phones or kitchen windows. Even on your darkest night in that room, there was always some little leak of light. A standby LED. A streetlight sneaking around the curtains. the moon bouncing sunlight into your backyard. What we call darkness on Earth is almost never truly dark. Out here, when the sun drops behind the planet, the stars switch on in full. The Milky Way appears as a pale band, a hazy river of light running across the sky. From a city, it almost disappears. From a quiet field, you might see it as a faint cloud. From above the atmosphere, it's sharp and intricate. Dust lanes and knots of brightness you never knew were there. Let me give you the clearest possible example. That cloud is not a separate object hanging over you. It's not fog. It's not a streak of vapor. It's not some distant galaxy. It is your galaxy. You are looking sideways through the flat disk of the Milky Way itself, staring along the crowded plain where most of the stars live. Every tiny shimmer in that band is a sun. Not dozens, not thousands, billions, all packed into a thin, rotating sheet of stars that your room, your ceiling, your whole life is already inside. And as we keep zooming out in the next part of this journey, that bright river of light will shrink until even our entire galaxy starts to feel as small as your room does now. As that bright river of light shrinks in your mind, we have to lay down one quiet but powerful rule. You can't understand where the whole Milky Way is going if you don't first understand where you are inside it. Place comes first. Motion comes second. Think about that for a second. If you dropped into a strange city with no map, no street signs, no idea which way was downtown, every car rushing past you would feel like chaos. The same is true for our galaxy. Before we talk about what might be dragging it through space, we need a clear picture of the city we live in and our tiny address inside it. Now imagine the Milky Way as a vast glowing city seen from high above in the darkness. In the middle, a blinding downtown of light, the central bulge crowded with old stars, dust, and gas. Winding out from it, spiral highways of starlight curve around and around, bright lanes where new stars are born. Beyond those, the glow fades into dimmer suburbs, scattered houses of stars stretching outward into the night. Let me give you the clearest possible example. Somewhere out in those suburbs, not downtown, not even on one of the main spiral highways, is us. The sun is sitting in a smaller feature called the Orion Spur, like a calm side street branching off between two big luminous freeways. It's a quiet neighborhood, about 26,000 light years from the noisy center, far enough away that we don't feel the drama of the galactic core, but close enough that the whole city's gravity still keeps us in orbit. Here's something that will make you smile. If the Milky Way were the size of a continent, stretching from one edge of your mental map to the other, our entire solar system would be smaller than a single coin lying somewhere in the suburbs. Not the city hall, not the main stadium, just a tiny coin on a side street lawn. And you? You'd be a speck on that coin, maybe a dust grain on the rim, sitting in your room, thinking about galaxy-sized questions. I want you to notice the pattern interrupt here. We started with your ceiling and your room. Now we're talking about a speck on a coin on a continent-sized city of stars. Same you, same brain, just a bigger picture. Because that's the strange situation we're in. A tiny speck on a tiny coin in a quiet suburb of a galactic city, trying to understand why the entire city itself is being pulled somewhere. In the next part of this long, calm journey, we'll zoom out again and watch not just one city, but whole clusters of galactic cities flow across the universe, all streaming toward something even larger in the darkness. So that's where we are, in a quiet suburb of a galactic city, watching the whole city slide through the darkness toward something bigger. Right away, I want you to know this. You do not need a physics degree to come with us. You don't need equations. You don't even need to like math. You just need a tiny spark of curiosity and a bit of time. This is going to be a long, calm journey. Big cosmic ideas, but surprisingly down to earth. In this video, we're going to move slowly, like your eyes adjusting in a dark room. First, everything will look like a blurry glow. Then, step by step, we'll bring the picture into focus until you can see the shapes hiding in that glow. Let me give you the clearest possible example. When we talk about the Great Attractor, we won't start with peculiar velocities or cosmic microwave backgrounds. We'll start with something like a map of rivers. Each galaxy will be a tiny boat, each one drifting along a curved path toward a low spot in the landscape. At first, you just see the boats moving. Then we'll slowly tilt the map, and you'll see the valley they're all sliding into. Think about that for a second. Right now, the entire Milky Way is one of those boats, moving at over 600 kilometers per second through space, and you never feel a thing. No wind, no shaking, just you, in a room watching a screen, while an invisible landscape of gravity tugs on everything. The promise here is simple. By the end of this journey, you'll be able to tell a friend what the Great Attractor is in one clear sentence. You'll be able to point at a picture of Laniakea, this vast supercluster about 500 million light-years across, and say, our galaxy flows along one of those lines. You'll be able to explain why our whole neighborhood is being dragged, not just by one mysterious region, but also by even larger structures hiding beyond it. Now imagine each new idea like a camera lens. We'll start wide and soft. A rough sketch, a simple image, a story about boats or cities of light. Then we'll gently twist the focus ring. The lines sharpen. The shapes become clear. Maybe a new label appears. Nothing jumps at you. Nothing is rushed. The only real prerequisite is a willingness to sit with scales that do not fit in your everyday life. Millions of light years, hundreds of thousands of galaxies. Times so long that a human lifetime is less than a frame in the movie. It can feel strange, even a bit unsettling. Here's something that will make you smile. That feeling of being small, it's actually a kind of relief. The universe is huge, and you are not in charge of any of this. As we keep zooming out, you may feel smaller than you ever have, and yet, somehow, more at home in the galaxy you were already riding through. In the next part, we'll start drawing that river map of galaxies and follow the flow lines straight toward the Great Attractor itself. To follow that river map, we need to do something a little unusual for a science video. I want you to actually change the room you're in, even if it's only in your imagination. Take a slow, deep breath in. Let it out, just as slow. Now imagine your hand reaching for the nearest light. A lamp, a switch on the wall, the brightness slider on your phone. Click. The first layer of light in your room disappears, and the shadows quietly expand to fill the space it leaves behind. If it's safe where you are, you can really do this. If not, we'll do it as a picture in your mind. Look around the room in your head. The ceiling, the shelves, the tiny glow from something that is always on. Now, imagine walking around and turning things off one by one. Click, the desk lamp. Click, the hallway light leaking under the door. Click, the little blue eye of a charger that never sleeps. You don't feel anything dramatic. No cosmic music starts playing. But as the light drains away, your eyes begin to work harder. At first, you still see the familiar shapes. A chair, a wall, your own hands. Then those shapes turn into outlines, edges without detail. Another minute, and even the outlines start to melt into a single soft darkness. Think about that for a second. This is the same room you were in a moment ago. The same air, the same furniture, the same Milky Way arcing above the roof. All that changed is how much light you're letting in. Let me give you the clearest possible example. If you've ever woken up in the middle of the night and stared at the ceiling, you know that slow shift when nothing becomes something again. And you suddenly realize you can see your own bedroom in the dark. Keep breathing. Slow in. Slow out. Maybe in your mind, only one source of light is left now. The faint rectangle of a window, or just the glow of this screen floating in front of you like a tiny artificial star. Everything else is sinking into a deeper shadow. You are approaching what we'll call true darkness. Not absolute, not the perfect black of deep space, but closer than what we usually allow ourselves to sit in during everyday life. Here's something that will make you smile. You're doing a very small version of what astronomers do with whole patches of sky, dimming the noise to see the faintest patterns. In this video, we're going to talk about invisible structures that drag entire galaxies around. To notice them, we first have to be comfortable in this quieter, almost dark place, where subtle motions and hidden flows finally start to show themselves. So, let's stay in that almost dark place, but make it even more familiar. I want you to look around the room you're in right now, or at least imagine it. The lights are off. The ceiling is just a suggestion above you. This feels like dark, the way we usually mean it in everyday life. But look closer. There's the tiny red eye of a standby LED on a charger. A soft blue blink from a router. Maybe the pale outline of your window, where streetlight sneaks through the curtains and paints a faint rectangle on the wall. Even the phone or laptop you're watching this on is a little island of light in the middle of your personal night. Think about that for a second. Now imagine you get up and walk to the safest cave you have at home. A closet, an interior bathroom. No windows, solid walls. You close the door. You turn off the light. For a moment, the darkness feels thicker, like someone turned up the volume on nothing. Then your eyes start to work. A thin line of light under the door. A ghostly glow around the frame. The tiny silvery outline of the towel rack or a shelf slowly appears. Let me give you the clearest possible example. You walk down into a basement with no windows at all, or an underground parking lot at night after most people have gone home. The door closes behind you. The air feels cooler. Your footsteps sound louder. At first, it's just a heavy blur. Then your pupils open wide, your vision switches into emergency low-light mode, and you start catching every stray photon you can. A glowing exit sign. A sliver of orange sodium light leaking down a ramp. The vague shine of a car's chrome bumper. On Earth, our darkness is always contaminated. We spill light everywhere with our lamps and screens, And even if we turned all of that off, the sky itself would still leak a soft glow down onto us. Starlight, air glow, the distant orange dome of a city over the horizon. We live on a planet that hates a perfect blackout, and yet we keep trying to imagine what real darkness might be like. So, let's go as far as we can without leaving the ground. You step outside into a wide, open field at night, far from any town. No houses, no billboards, just grass, maybe a fence, and a big, quiet sky. At first, it feels like someone finally dimmed the whole world properly. Then the stars come out. The Milky Way rises as a pale river overhead, a slow, cloudy band you can almost mistake for a high, thin cloud, until your eyes adjust, and you realize it's made of countless tiny points. Here, your room has expanded to the size of the sky, and the ceiling is made of stars. It's beautiful, and it feels deep, but this is still just the lobby of cosmic night. Beyond that soft river of light, the real darkness of space is waiting, and it's in that deeper shadow that something huge is dragging our entire galaxy along. Out in that field, under that pale river of the Milky Way, something very quiet and very strange is already happening inside your own head. Your pupils open. The little sensors in the back of your eyes change their chemistry. In a few minutes, you become a different kind of creature in the dark. Your eyes are performing a kind of biological magic trick. In bright daylight, they are stingy, throwing away most of the incoming light so you aren't overwhelmed. But in real darkness, they go into emergency mode. They start amplifying tiny amounts of light millions of times, stacking faint signals until a star that would be invisible in your living room suddenly becomes obvious in the sky. Think about that for a second. Let me give you the clearest possible example. You're standing there, and you spot a very faint star near the edge of your vision. It looks like almost nothing, just a tiny pinprick. That photon left its star hundreds, maybe thousands of light years away. It crossed the empty spaces between stars, slipped through the top of Earth's atmosphere, dodged clouds, and, out of all the places it could have landed, it ends its journey in your retina. One tiny packet of light, one tiny electrical whisper in your brain. Here's something that will make you smile. Some of the faintest stars you can see with your naked eye have been traveling toward you since long before humans built cities, or wrote down stories, or even knew what a galaxy was. And yet, on a random night, in an ordinary field, those ancient travelers just quietly report in to you. I made it. There is something oddly polite about that. Now imagine you let your gaze drift to that hazy band crossing the sky. It doesn't look like individual stars at first, more like someone brushed a thumb of smoke across the darkness. Here's something that will make you smile. That soft band is your naked eye proof that you are inside a galaxy. You are not outside looking in at a picture. You are standing in the disk itself, looking along its crowded plane. Almost no one walking under that sky is thinking in that moment, I am inside a rotating disk of hundreds of billions of stars orbiting a black hole. You might be wondering, what's for dinner? You might be scrolling on your phone. And yet, above you, that whole glittering city of stars is turning, and you are strapped to one tiny apartment in it. This is going to be a long, calm journey, and right now, we're still close to home. If this faint band is just our local neighborhood in the Milky Way, what does the universe look like when we zoom out far enough to see what's dragging the entire disk itself through the deep darkness? To answer that, we need a simple map. Not a perfect scientific diagram with every detail labeled, but a picture you can carry around in your head. I want you to be able to close your eyes in a quiet room and actually feel where you are inside the Milky Way. Now imagine you're looking at our galaxy from far above, with the lights in the universe turned down low. The Milky Way is not a sphere. It's a disk, flat, wide, and thin, like a glowing, spinning pancake laid out in the darkness, with a bright, swollen center. That central bulge is the crowded downtown, packed with stars, gas, and dust, shining so intensely that, from the side, it would look like a small ball stuck in the middle of a coin. From that bulge, great spiral arms unwind and curve around, like broad, starry highways. They're not sharp lines. They're more like glowing traffic jams of stars, gas, and dust, wrapped in slow motion around the galaxy. Along those arms are the busy construction zones of the Milky Way, where clouds of gas collapse and new stars flare into light. Think about that for a second. Whole nurseries of suns scattered along these lanes. Our sun, though, is not parked on one of the biggest highways. It sits in a quieter side street, a smaller feature called a spur, tucked between two of the major arms. Let me give you the clearest possible example. If those main arms are like the big ring roads around a city, the sun lives on a calmer connecting road between them. Still part of the city, still lit by the glow, but not right in the middle of the rush. Here's something that will make you smile. If the Milky Way disk is about 100,000 light-years across, its thickness is only about 1,000 light-years. That's 100 to 1, like a coin compared to its diameter. A cosmic DVD in a very, very large player. Our whole stellar city is astonishingly flat compared to how wide it is. You are not at the center of this disk. You're about 2/3 of the way out from the middle, in what astronomers sometimes call the galactic suburbs. It's a relatively stable, calm, not too crowded region. No raging black hole right next door. No extreme starburst lighting up the sky. Just a comfortable orbit in a middle-class neighborhood of stars. Kind of nice, isn't it? This flat disk isn't floating alone either. It's embedded in a much larger, invisible halo of matter that stretches far beyond the light you can see. In this video, we're going to treat this picture as our base layer. A spinning, glowing pancake inside an unseen bubble. Every strange pull and hidden drag we talk about next is going to act on this disk, on that halo, and on the tiny suburb where you live. So now that you know the shape of your galactic city, what happens when the whole pancake starts sliding through the universe, tugged by something even bigger? So when we say the whole pancake is sliding through the universe, we should pause and ask, how fast is the tiny suburb on that pancake already moving? And how do you fit your own quiet room into that motion? You know the Earth orbits the Sun in 1 year. You feel the rhythm of that in seasons, in birthdays, in school calendars. But the Sun itself is not parked in space. It is on a much bigger track, looping around the center of the Milky Way in a vast, almost unimaginable circle. Astronomers call one of these loops a galactic year. It takes the Sun roughly 200 to 230 million of our normal years to go around once. Think about that for a second. When the dinosaurs were walking through ancient forests, the sun was in a completely different part of its path around the galaxy. Let me give you the clearest possible example. The sun has been shining for about 4.6 billion years. Divide that by a roughly 225 million year galactic year, and you get only around 20 or so laps. In the entire lifetime of the sun, our solar system has gone around the galaxy maybe 20 to 25 times. That is the slow, deep clock our whole planetary story has been ticking to. Now imagine turning that huge circle into speed. To keep its orbit, the sun is racing around the galactic center at about 220 kilometers every second. Not every hour, every second. In the time it takes you to blink, we've moved hundreds of kilometers along that path. Here's something that will make you smile. You don't feel any of it. There's no galactic wind in your hair, no low rumble under your chair. You might just be sitting in a room, watching this on a screen, feeling completely still. And yet you, the walls, the ceiling, every lamp and coffee mug you can see, are all strapped to this star doing 220 kilometers per second through a glowing city of light. I want you to picture it like a train ride. You're in a window seat on a train that takes 200 million years to make one loop around a single enormous city. The buildings are clusters of stars. The streetlights are nebulae. The downtown is a bright, crowded bulge of starlight. Outside your window, the scenery changes so slowly that no single human could ever notice it. Our daily cycles are tiny ripples on top of that. A 24-hour spin of Earth, a 1-year trip around the sun. All of human history is just a thin scratch along the edge of one galactic year. This is going to be a long, calm journey, whether we pay attention or not. So here's the real puzzle. If we're already moving this fast around the Milky Way, what does it even mean to say that the entire galaxy is also being dragged somewhere else, through something even larger than this city of stars? To answer that, we have to step back from the bright parts of the Milky Way and walk into the darkness around it. I want you to picture the galaxy the way you've probably seen it in posters or screensavers. A glowing spiral of light, a flat disk with a crowded center and delicate arms. It feels complete, like that's the whole thing. But that shining disk is just the downtown at night. The real city is bigger, quieter, and mostly invisible. Now imagine flying straight up, away from the Milky Way's lit-up streets of stars. The disk shrinks to a thin coin of light. Around it, stretching several times farther in every direction, is something you can't see at all. A vast, roughly spherical halo of dark matter. No stars, no glowing gas, just mass, wrapped around the galaxy like an enormous, transparent cushion. Think about that for a second. Most of the Milky Way's mass is not in the stars you see in time-lapse sky videos, or in the glowing gas clouds we love to photograph. It's in this unseen halo. The downtown lights are impressive, but the suburbs, the highways, the foundations, the pipes in the ground, that's what really holds a city together. The dark halo is that hidden infrastructure. Let me give you the clearest possible example. When astronomers measure how fast stars orbit in the outer parts of the disk, far from the crowded center, they expect those stars to slow down, the way planets do as you move away from the sun. But they don't. They keep whipping around too fast for the visible mass to keep them bound. It's like watching cars on the edge of a city going highway speeds on what looks like empty farmland. Something heavy has to be there, pulling on them. We call that extra pull dark matter, and the halo it forms around the Milky Way is huge. In a calm way, it changes everything. Our galaxy isn't just a flat pancake of light. It's a node in a much larger dark scaffold, a kind of three-dimensional framework of invisible mass that links us to other galaxies. Here's something that will make you smile. When we say the Milky Way is part of a local group of galaxies, or a cluster, or an enormous supercluster like Laniakea, what's really doing the social networking isn't the pretty starlight. It's these overlapping dark halos, tugging and merging, guiding galaxies along like leaves in a slow cosmic river. And that brings us back to the word dragging. When something drags our galaxy, it's not yanking on the thin disk you see in pictures. It's pulling on this deep, extended halo, along with the halos of our neighbors, toward even larger clumps of mass. In the next part, we'll follow that pull out into the cosmic web and meet the mysterious regions of space that are steering our entire galactic city through the universe. So let's zoom out one more step. That invisible halo of dark matter around the Milky Way isn't sitting alone in the darkness at all. It's part of a small gravitational neighborhood, a kind of local cosmic town. Astronomers call it the local group. More than 50 galaxies, all bound together by gravity, all sharing the same slow fall through space. Two of them dominate the scene: our Milky Way and another great spiral made of hundreds of billions of stars. You've probably seen its picture on a screen without quite realizing you are looking at our nearest giant neighbor. That neighbor is the Andromeda Galaxy. Now imagine stepping out of your room, out of the Milky Way's disk, and drifting into the dark between galaxies. About 2.5 million light-years away, you'd see Andromeda hanging in the black, like a tilted, glowing whirlpool, just a bit larger than our own spiral. Think about that for a second. The thing we are inside right now has a sibling, and they're staring at each other across intergalactic space. Here's something that will make you smile. Those two giant spirals are not politely keeping their distance. They're on a slow-motion collision course. Very slow. In about 4 billion years, the Milky Way and Andromeda will drift together, their stars weaving past each other like swarms of fireflies, until the two disks merge into one new, larger galaxy. No crash sound, no cinematic fireball, just gravity, working patiently over unimaginable time. But the local group isn't just these two big show-off spirals. Around them, dozens of tiny dwarf galaxies swarm like fireflies around lanterns. The large and small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light, are two of our closest companions, looping around the Milky Way in stretched, slow orbits. Other dwarfs cling to Andromeda, little smudges of stars wrapped in their own tiny halos of dark matter. I want you to picture an archipelago, a scattered string of islands in a vast, dark ocean. Each island is a galaxy, a city of stars, gas, and dark matter, lit from within, but surrounded by emptiness. The Milky Way is one island. Andromeda is another, a bit bigger, just over the horizon. The dwarf galaxies are the smaller rocks and islets, some bright, some barely more than shadows. Together they form our local group, a small cluster of islands floating in a cosmic sea. In this video, we're going to keep stepping back from the familiar shore, because even this entire island group, containing everything you have ever seen or loved, is not at rest. The whole archipelago is being carried along by a much larger current in that cosmic ocean, pulled by distant structures we can barely see. What kind of current can move an entire group of galaxies? That current has a name. Our small local group, that island chain of a few dozen galaxies, is actually part of a continent of islands. Astronomers call it the Laniakea supercluster, a region of space about 500 million light-years across, containing roughly 100,000 galaxies. Think about that for a second. Every fuzzy smudge in a deep telescope image might be an entire galaxy. And Laniakea is a whole landscape made out of those smudges. Now imagine trying to map a landscape in the dark. You can't see the hills or valleys, but you can watch how water flows. That's what astronomers did with Laniakea. They didn't just mark where galaxies are, like pins on a flat map. They measured how those galaxies move, how each one drifts relative to the smooth expansion of the universe. And they traced those motions the way you'd trace streams running down a mountain. Let me give you the clearest possible example. Picture a huge invisible bowl carved into space-time. On the surface of that bowl are tens of thousands of galaxies. Each galaxy is like a leaf floating on a thin film of water. The water is slowly sliding down the sides of the bowl, and the leaves slide with it. If you draw little arrows showing which way the leaves are moving, all the arrows curve and bend, and in the end, they point toward the deepest part of the bowl. Those arrows are what astronomers call flow lines, and when they drew the flow lines for our region of the universe, something beautiful appeared. All across Laniakea, from scattered clusters and lonely groups, the paths of galaxies curve inward. They form a giant cosmic river system. Tiny tributaries merge into streams, streams merge into rivers, and all those rivers flow toward a central gravitational basin. Here's something that will make you smile. Our Milky Way, which already feels unimaginably big, is just one thin blue line in that diagram. One little stream in a drainage map of the cosmos. We, along with the Andromeda Galaxy and our other neighbors, are drifting along that line toward a region we call the Great Attractor, buried behind the bright band of the Milky Way's own light. You don't feel it. There's no wind in your room, no tug on your chair, and yet your entire galaxy, your entire local group, and tens of thousands of other galaxies are sliding together into that basin, like leaves on a slow, dark river. I want you to sit with one last idea. If our whole supercluster is defined not by where galaxies are, but by where they're going, what does it even mean to be at rest anywhere in the universe? In the next step of this journey, we'll follow that river toward the heart of the pull itself. So we follow that slow, dark river, not with a boat, but with our minds. You're still in your room, maybe with a screen glowing nearby, but in your head we're drifting along those flow lines of galaxies, watching the Milky Way slide toward something in the distance, something we didn't even know was there for most of human history. Astronomers gave it a dramatic name: the Great Attractor. It isn't a single shining beacon. It's more like a patch of sky, roughly in the direction of the constellation Norma, where the motion of thousands of galaxies seems to bend and lean. When we map their paths, they don't just wander. They tilt. They curve. They all seem to be falling toward that same region, as if there's a cosmic sinkhole tugging at the fabric of their journeys. Now imagine you're expecting a monster at the center, a gigantic black hole, a single clear culprit. But the Great Attractor isn't like that. It's not one object we can point at and say, "There, that's the thing." It's a crowded region of space, full of galaxy clusters, hot gas, and a huge amount of dark matter. All those masses together make a deep gravitational basin, and our whole Laniakea supercluster is sliding gently down its slopes. Think about that for a second. Here's the strange part. From Earth, the Great Attractor sits right behind the thickest part of our own galaxy. The Milky Way's disk stretches across the sky like a glowing river of stars. But along that river is also a dense curtain of dust and gas. Astronomers call that blocked-off band the Zone of Avoidance, because visible light from beyond it is muffled and scattered. We live behind our own galactic blinds. So when early galaxy surveys tried to map the universe, they saw something odd. On one side of the sky, galaxies seemed to be drifting toward this hidden region. On the opposite side, their motions hinted at the same pull, like leaves on a pond, all sliding toward a drain you can't see under the surface. Let me give you the clearest possible example. Imagine plotting thousands of galaxies as tiny arrows, each arrow showing its motion. A surprising number of those arrows lean toward Norma, almost like they're all listening to a quiet, distant whisper. For a while, it was tempting to treat the Great Attractor as the main character. Mystery solved, story wrapped. And yet, as we slowly peeled back the Milky Way's veil with radio waves and X-rays, another bigger pattern started to emerge. The sinkhole we'd found was real. But behind it, farther out in the darkness, something even more massive was waiting to be uncovered. But behind it, farther out in the darkness, something even more massive was waiting to be uncovered. To see it, we had to stop looking at galaxies for a moment and look at the universe itself as a kind of background wallpaper. Right now, wherever you are, sitting in a room or walking outside under city lights, you are bathed in a very old glow, the cosmic microwave background. It's the cooled afterglow of the Big Bang, a faint wash of microwave light filling every corner of space. If we were perfectly at rest with respect to this ancient glow, it would look the same in every direction. No preferred spot, no special arrow in the sky, just an almost perfectly uniform temperature, like a cosmic fog that doesn't care which way you turn your head. Think about that for a second. A universe with no headwind at all. But that's not the universe we live in. When satellites like COBE, WMAP, and Planck mapped this background in detail, they found a very simple, very clear pattern written across the whole sky. One half looks ever so slightly hotter and bluer. The opposite half looks slightly cooler and redder. It's called a dipole, and it's the universe's way of telling us, you are moving. Let me give you the clearest possible example. Imagine you're riding a bike on a still day. The air in the park isn't doing anything dramatic, it's just there. But as you speed up, you feel a breeze on your face. The air in front feels colder, sharper. Behind you, it's calm. The air didn't suddenly decide to blow at you. You created the wind by moving through it. The cosmic microwave background works the same way. The light in front of our motion gets ever so slightly compressed, nudged to higher energy, so it looks a bit hotter. Behind us, it's stretched, cooled, relaxed. That tiny temperature difference, only a few parts in 1,000, is our cosmic headwind. When astronomers measure that dipole, do the slow, careful math, and translate temperature into speed, they get a remarkable number. The Milky Way, together with our little local group of galaxies, is sailing through this sea of ancient light at about 600 to 630 kilometers per second, aimed toward a specific patch of sky in the direction of the constellation Hydra and the region of the Great Attractor. You don't feel it. Your room is quiet, and yet you're part of that drift. Here's something that will make you smile. You can close your eyes right now, and the universe is still whispering your motion to you as a temperature pattern. You are, in a very literal sense, moving relative to the afterglow of the Big Bang. Now, imagine what kind of invisible landscape could pull an entire galaxy along at that speed. In the next part, we'll start to trace that flow across hundreds of millions of light years into the true continent our Milky Way lives on. We've been talking about this huge quiet drift of the Milky Way through the afterglow of the Big Bang. You're already moving with the fabric of space itself, Habzada, but on top of that smooth slide, something messier is happening. I want you to picture the universe on the very largest scales as surprisingly simple. Galaxies are like tiny dots painted on the surface of an inflating balloon. As the balloon swells, every dot sees every other dot drifting away. No one has rockets on. No one is steering. Space just stretches, and the distance grows. Think about that for a second. If that was the whole story, you could describe a galaxy's motion just by how far away it is. But it isn't the whole story, because gravity never got the memo about staying neat and even. Some regions ended up a little denser, a little heavier, and they pull harder. So each galaxy doesn't just ride the balloon's expansion. It wiggles. It falls a bit toward its neighbors. It gets tugged by clusters and filaments of dark matter. That extra local motion has a calm name: peculiar velocity. Peculiar here doesn't mean weird in a bad way. It just means on top of the general expansion. Let me give you the clearest possible example. Imagine you're sitting in a boat on a wide, slow river. The whole river is flowing downstream. That's the expansion of the universe. Now add in the details. Little whirlpools around rocks. Side currents that nudge you toward one bank. A hidden bend that speeds the water up. Those swirls and sideways pushes are peculiar velocities. You and every other boat are all carried downstream together. But each one also has its own small, stubborn path. Astronomers actually measure this. They look at a galaxy's redshift, the way its light is stretched as space expands, to get a speed from the river's current. Then they measure its real distance using other tricks. How bright certain standard stars are, or how a particular kind of exploding star behaves. If the galaxy's redshift says it should be moving at one speed for its distance, but the distance check disagrees, that mismatch is its peculiar velocity. Here's something that will make you smile. Our whole Milky Way, with all its stars and darkness and slow-turning spiral arms, has a peculiar velocity of about 600 kilometers per second relative to that cosmic afterglow. That's not the smooth balloon talking. That's the river's hidden rocks and bends. It means some nearby massive landscape of galaxies and dark matter is yanking on us, hard. You don't feel it. Your room is quiet. Your pen still falls straight down. And yet the entire galaxy is part of a vast, invisible flow. In the next part, we'll follow that flow out into the larger continent of galaxies around us and meet the mysterious Great Attractor that seems to be dragging our whole neighborhood through space. So let's actually try to see this invisible pull. I want you to imagine the universe turned into a quiet, dark 3D grid. No labels, no dramatic music, just tiny points of light, each one a galaxy, floating in the black. Astronomers take real measurements of distance and motion and drop those galaxies into this map, not as fuzzy spirals, but as clean dots hanging in space. Now imagine they give each dot a little arrow. The arrow doesn't show the smooth expansion of the universe. It shows the extra motion on top of that, the way each galaxy is drifting relative to the general cosmic stretching. These are called peculiar velocities, but the picture they make is anything but peculiar. When you step back and look at millions of arrows at once, something beautiful happens. They start to line up. You see streams, whole swarms of galaxies, all their arrows leaning in roughly the same direction, as if someone tilted the entire room and everything began to slide across the floor. Think about that for a second. Every arrow is one island of hundreds of billions of stars, and yet they behave like grains of sand in a slow cosmic landslide. Let me give you the clearest possible example. Picture a topographic map, those thin, looping contour lines that show hills and valleys. Rain doesn't care about the lines. It just flows downhill. But if you trace the paths of raindrops, they reveal the shape of the land. In space, the galaxies are the raindrops. Gravity draws the contour lines. The height is gravitational potential, and galaxies flow down into invisible valleys called basins of attraction. On a flow map, those basins stand out. These arrows bend toward them, curve around them, spiral in. One of the biggest features in our part of the cosmic landscape is what we call the Great Attractor. When astronomers plot the arrows for our local group, for the Milky Way, for our neighboring galaxies, they all lean the same way. Our flow line points straight toward that region, buried behind the thick band of the Milky Way's own light. You don't feel that in your chair. Your pen still falls toward the floor, not toward the Norma cluster hundreds of millions of light years away. And yet, in these maps, our entire galactic neighborhood is clearly sliding down the same gravitational slope, joining a larger river of galaxies that defines the Laniakea supercluster around us. Here's something that will make you smile. For a while, we thought that was the end of the story. We're falling into the Great Attractor. Roll credits. But when astronomers extend those flow lines farther out, they don't stop. The arrows keep going, bending past the Great Attractor, pointing on toward an even deeper concentration of mass. In the next part, we'll follow those lines into the distance and meet the something bigger that's tugging on all of this at once. So we follow those invisible arrows, gliding past the Great Attractor as if it were just a bend in a river and not the destination. The flow lines don't crash into a wall. They keep streaming on, farther into the darkness, towards something even larger stitched into the cosmic web. Now imagine zooming the map out again. The Milky Way shrinks to a dot. Laniakea becomes a faint swirl. And out there, hundreds of millions of light years away, a new bright knot appears. That knot is the Shapley supercluster. It's not just one cluster of galaxies, but a whole crowded district of them, piled together in space like city blocks pressed into a glowing downtown. I want you to picture this as a web of light. Each filament is a chain of galaxies, with dark matter as the hidden scaffolding. At the crossing points, the web thickens. Shapley is one of those crossings turned up to maximum. Tens of thousands of galaxies, vast clouds of hot gas, an ocean of dark matter heavy enough to bend the paths of entire galaxy clusters passing nearby. Think about that for a second. Let me give you the clearest possible example. If you could float above this region and look down with impossible eyes, you'd see galaxies as tiny sparks drifting along curved tracks, like leaves on slow, invisible currents. Follow enough of those tracks backward, and many of them don't end at the Great Attractor. They arc beyond it, sink in deeper into Shapley's wider gravitational valley. When astronomers extended their flow maps to include that far-off knot, something clicked. The directions of many galaxy motions lined up more cleanly. It was as if the Great Attractor were just the nearer slope of a much larger basin, and Shapley was the deeper center, quietly pulling from behind the curtain of distance and time. Our whole region of the universe seems to be sliding ever so gently down that larger curve. Here's something that will make you smile. You're sitting in a room, maybe with a lamp or a screen glowing, and yet your chair, your walls, your entire life are being carried along by a galaxy that's responding to a supercluster you will never see with your own eyes. You didn't sign up for this ride, and yet you're strapped in all the same. If Shapley, so far away, can still reach across hundreds of millions of light years to tug on us, what else is out there, just beyond the edge of our current maps? How many even bigger knots in the web are shaping our path without a name yet, or still hidden behind our own Milky Way's light? In the next part, we'll push our view out again and ask whether Shapley is the final destination, or just another stepping stone on an even larger journey. So, when we zoom past Shapley and those named superclusters, what does the whole thing look like from far, far outside? Now imagine turning down the brightness of every individual galaxy and turning up the contrast on the invisible scaffolding underneath. A new picture appears. The universe stops looking like random glitter and starts looking like a web. This cosmic web is a vast network of filaments, stretching for hundreds of millions of light years. Along each filament, galaxies and clusters string together like tiny beads on enormous invisible threads. In between them are giant voids, huge regions that are almost empty compared to the rest. Think about that for a second. We used to think of space as mostly nothing, with the occasional galaxy. On the largest scales, it's the opposite. The structure is the web, and the emptiness has a shape. Let me give you the clearest possible example. I want you to picture a kitchen sponge or a piece of foam. Hold it up under a bright light in a quiet room. You see a network of solid edges and corners, and inside each cell, a bubble of almost nothing. In the universe, the galaxies live along those solid edges, on the surfaces and at the intersections. The interiors of the bubbles, the voids, are the dark, underfilled parts, where there are hardly any galaxies at all. Gravity, acting slowly over billions of years, carved this sponge. At the beginning, matter was spread almost evenly. Tiny, tiny bumps in density gave gravity a head start. The slightly denser spots pulled in more matter, which made them denser still, which pulled in even more. Over time, matter slid off the insides of the bubbles and collected in the filaments and knots. It's like watching rain on a window, when droplets merge and run along the same paths, leaving clear streaks behind. Here's something that'll make you smile. Our grand Laniakea supercluster, with its poetic name and its 100,000 galaxies, is just one lumpy feature on a single strand of this web. Our local group is a smaller knot on that strand. The Milky Way is a thread inside that knot. You, right now, are sitting in a room on a planet circling a star that is part of one bright grain of foam on the edge of a cosmic bubble. So when we say something is dragging our galaxy, we're not being pulled by a cosmic hand. We're sliding along the sloping strands of this web, flowing toward deeper gravitational wells where the filaments cross. The Great Attractor, Shapley, whatever lies beyond them, they're just downhill. In the next part, we'll follow that downhill flow more closely and ask where, if anywhere, this long, calm journey is really trying to take us. So let's zoom back in for a moment, from those giant downhill slopes of the cosmic web, all the way to you. Right now, wherever you are, you're sitting in a room, or a car, or on a train, maybe under a soft pool of light, or in the glow of a small screen. It feels still. It feels local. It feels like the whole story. But it isn't. Not even close. Under your feet is Earth, a ball of rock and air and water, spinning once every day, swinging around the sun once every year. Think about that for a second. Your quiet chair is already riding a planet doing 30 kilometers every second around its star. And that star, our sun, is just one ordinary light among hundreds of billions in the Milky Way. Now, imagine the Milky Way again as that flat, hazy river of starlight across the darkness. The sun is tucked into a tiny side street of one spiral arm, circling the galactic center at hundreds of kilometers per second. Let me give you the clearest possible example. Compared to the full disk of the galaxy, our entire solar system is like a dust mote drifting somewhere in the middle of a vast, spinning city. Pull back another step. Our galaxy is not alone. It's one of just a few dozen in the local group, a small neighborhood of galaxies orbiting and tugging on each other. That whole group is just a bright knot inside Laniakea, a supercluster about 500 million light-years across, a huge basin where over 100,000 1,000 galaxies flow together along invisible slopes of gravity. And even that isn't the edge of the picture. Laniakea itself is just one patch in the larger cosmic web, where filaments of galaxies stretch for billions of light years, like glowing veins of light running through almost endless darkness. Each layer you step out to is not just a little bigger. It's bigger by orders of magnitude. Your everyday scale doesn't just shrink. It almost vanishes. Here's something that will make you smile. All the things that feel huge in your life. A deadline, an awkward message, that one embarrassing memory from years ago, do not even make a ripple in these flows. The Great Attractor does not care about your inbox. Shapley does not notice your laundry. That might sound cold, but it's actually a kind of freedom. Your smallness here is not an insult. It's a quiet permission slip. You are free to exist, to worry, to relax, without the weight of the galaxy on your shoulders. The rivers of galaxies will keep streaming along their paths, whether you answer that text right now or not. And yet, you are not separate from any of this. The exact same gravity that bends the paths of galaxy clusters is holding you to your chair. The same invisible pull that guides the Milky Way toward those deeper wells is what makes a dropped pen fall to the floor. I want you to picture that. One simple idea, one single kind of pull, acting smoothly from your hand all the way out to the edge of the cosmic web. So now that we've slowly mapped your cosmic address, from room to planet to galaxy to web, we can finally ask a deeper question. If every layer is moving, if there's no ultimate background to sit still against, what does it really mean to move through a universe with no true rest? If every layer is moving, if there's no ultimate background to sit still against, what does it really mean to move? Or to rest? Right now, your body feels quiet. Your hands, your chair, the walls of your room all agree. You're not going anywhere. But that calm is local. It's a tiny peace treaty in the middle of a much bigger storm. Motion in physics is always about comparison. You can be still relative to your desk, while racing relative to the moon, drifting relative to the Milky Way, and falling relative to the vast web of galaxies that surrounds us. Think about that for a second. Let me give you the clearest possible example. Imagine you're sitting on a train, perfectly still in your seat. A second train slides by outside. For a moment, with no ground in sight, you can't tell who's moving. You, them, both. That little moment of confusion is the whole universe, squeezed into a station window. In your room, you are at rest relative to the floor. But the floor is spinning with Earth's rotation, about 1,600 kilometers per hour at the equator. The whole planet is looping around the sun at about 30 kilometers every second. The sun, with all its planets, orbits the center of the Milky Way at around 230 kilometers per second. And the Milky Way itself is drifting through the larger darkness, tugged by invisible structures. You don't feel any of this. There's no cosmic seatbelt sign blinking in the corner of your screen. So if everything is always in motion, is there any special frame where you could say, "Here, this is truly at rest"? Cosmologists use something close. They look at the cosmic microwave background, the faint afterglow of the Big Bang, which fills all of space like a soft, uniform light. If you're moving through it, this glow looks a tiny bit warmer in the direction you're heading and cooler behind you. Here's something that will make you smile. When we do this with our own galaxy, we find that the Milky Way and its neighbors are rushing at over 600 kilometers per second relative to that ancient light. Even compared to the universe's baby picture, we are not sitting still. We are plunging. Now imagine trying to find a truly quiet corner in a river where every drop is being pulled by gravity. Even the still pools are just slower currents. In the same way, our idea of rest is a useful illusion, local, comfortable, and quietly broken by the larger flows of the cosmic web. So when you say, "I'm not moving," what you really mean is, "I'm not moving much compared to the objects near me." On the scales that matter to your coffee cup, that's enough. On the scales that matter to galaxies, it's like claiming a leaf is still while it rides a tide across an ocean. And we haven't even asked yet what exactly that ocean is dragging us toward. So let's slow this ocean down and really watch one leaf. You, right now, sitting in a room or on a train or lying in bed staring at the ceiling. You feel still. Your coffee cup feels loyal. But you and that cup are already riding a whole stack of motions. Let me give you the clearest possible example. I want you to picture the Earth as a smooth, dark ball floating in space, a faint band of city lights, some clouds, a thin line of atmosphere glowing in the sun's light. Now imagine a tiny dot on that surface. That's you. As Earth spins once every 24 hours, that dot is being swung around at hundreds of meters per second, just from the rotation alone. Think about that for a second. If you're near the equator, you're doing over 1,600 kilometers an hour, sideways, in the darkness, with no sound and no warning. If you're closer to the poles, it's a bit slower, but still fast enough that if a plane did it, you'd brag about the ticket. Yet your room feels perfectly calm. No wind, no tilt, just quiet motion you never notice. Now zoom the camera out. Keep Earth's spin, but pull back until the sun comes into view. Our spinning ball is also tracing a wide circle around that sun at about 30 kilometers per second. The daily spin becomes a small, wiggly loop riding on a much larger ring. Every day, that little dot that is you draws a spiral in space. Spin plus orbit, layered together. Pull back again. The sun stops being the center and becomes just another light in the Milky Way. Our whole solar system orbits the galaxy's center at around 220 kilometers per second. On this scale, that nice, neat path around the sun turns into a tiny squiggle carved into a huge, sweeping curve around the galactic core. Or here's something that will make you smile. Your entire lifetime is less than a millimeter on that galactic track. If we shrank the orbit to the size of a city, one more layer. Zoom out until the Milky Way itself is just a thin smear of light among thousands of other galaxies. The whole disk, every star you've ever wished on, is now moving at roughly 600 kilometers per second, plunging toward the region we call the Great Attractor and beyond. Compared to that fall, all the earlier motions are like tiny vibrations on a drifting leaf. This is going to be a long, calm journey, because even that stacked motion isn't the end of the story. since the very landscape we're falling through is slowly changing shape. And the real question is what's reshaping it in the first place. So let's do something our bodies can't. Let's speed time up until a human lifetime is just a flicker, and the Milky Way's motion finally becomes visible. Now imagine you press play on a time lapse that runs for hundreds of millions of years, like pointing a camera at the sky and leaving it on for an entire galactic year. You don't feel it. The room around you looks still. But in this fast-forward universe, the stars above are no longer quiet pinpricks in the darkness. They wheel overhead like glowing leaves in a slow whirlpool, tracing huge curves as the sun carries you around the center of the galaxy. Think about that for a second. Every familiar star pattern you know is balanced on top of that invisible carousel. Let me give you the clearest possible example. Take Orion. In our ordinary lives, it's a steady winter picture, a hunter frozen on your ceiling of sky. In the time-lapse, his belt stretches, one star drifting away, another sliding down. Cassiopeia's neat W slumps and unhooks. The Big Dipper spills. Over a few 100 million years, constellations don't just shift, they warp and dissolve as the sun threads its path through the Milky Way. And as the whole galaxy drifts along the cosmic web, here's something that will make you smile. In this video, we're going to treat the Milky Way itself like one more constellation. In the sped-up sky, that pale river of light across the night doesn't stay politely in place. The bright band of the disk slowly tilts, rolls, and reorients. Sometimes it's a clean arc from horizon to horizon. Sometimes it's a diagonal slash. Sometimes it's a low, thick smear hugging the edge of the world. You are watching your address inside the disk change, your angle to the spiral arms shifting as we move. As the Milky Way turns and falls, the backdrop behind it changes too. Those tiny fuzzes we call galaxies and clusters creep across the black like distant ships on an ocean. The region we call the Great Attractor, and farther still, the massive Shapley concentration, don't leap dramatically in the frame. Instead, over immense stretches of this movie, more and more flow lines of galaxies seem to lean their way. Their pull gently reshapes the large-scale pattern of lights in the far background. I want you to notice what that means. The sky you grew up with, the one you might look at through a bedroom window or from a dark field, is just one frame in a very long, very slow movie about motion. Our constellations are temporary sketches. Our Milky Way is a drifting city of light. And the whole scene is being nudged by structures so large we only see their effects. In the next part of this journey, we'll step back again and ask what exactly is doing that nudging. We just asked, what could be nudging an entire drifting city of light like the Milky Way? But there's a twist. When we turned to look in the direction that pull was coming from, our own galaxy quietly stepped in front of the camera. Astronomers even have a calm, slightly dramatic name for this: the Zone of Avoidance. I want you to picture the night sky as a giant dome around your room. Most of it is clean and sharp. Distant galaxies show up as tiny smudges of light. But along the plane of the Milky Way's disk, the view suddenly turns crowded and muddy, as if someone smeared fog across the glass. When you look toward the Milky Way's band on a dark night, you see millions of stars packed together. It feels bright, it feels open, and yet invisible light, that same direction, is actually one of the most hidden parts of the sky. Dust clouds in our own disk soak up and scatter starlight. Behind that glowing river, distant galaxies are trying to send us their light, and we mostly just see our own ceiling. Think about that for a second. We live inside a thin, dusty disk. We're trying to look out through the side of it. It's like lying on the floor of a very crowded theater, trying to see the exit sign through rows and rows of seats and people. You can tell something is out there from the way everyone is leaning, but your direct line of sight is a mess. Early galaxy surveys had this exact problem. On photographic plates, the sky looked full of galaxies in most directions, but right where the motion of the Milky Way seemed to be pointing, there was a huge blind strip, a dark lane of uncertainty. Was the Great Attractor hiding there, or were we being pulled by something even farther away? The map had a missing piece right where we needed it most. So astronomers changed the kind of light they used. Visible light was blocked, but infrared light can slip through dust more easily, and radio waves can cruise through almost as if the dust isn't there at all. Let me give you the clearest possible example. In infrared surveys, that murky zone began to thin out. In radio, galaxies started popping up like lights turning on in a foggy room. Slowly, clusters emerged, including a dense one called the Norma cluster, sitting close to the suspected core of the Great Attractor. Here's something that will make you smile. To understand what was dragging our galaxy, we had to admit that our galaxy itself was in the way. Our own Milky Way, the thing we're trying so hard to understand, literally blocks our view of what is pulling it. So to keep going, we have to get creative with light, with maps, and with how we read motion. And in the next part of this journey, we'll follow that motion out beyond the Great Attractor, into something even larger. So we dim the glare of our own galaxy, peel back the Milky Way's bright band, and ask, what exactly is sitting in that hidden patch of sky, tugging on us so hard? Right near the center of the Great Attractor region, buried behind dust and stars, sits one of the main suspects, the Norma cluster. Now imagine a city of galaxies, not a few dozen, thousands. The Norma cluster, also called Abel 3627, is one of these deep cosmic downtowns, a crowded knot of galaxies all orbiting a shared center of gravity. Each galaxy holds billions of stars, clouds of gas, and a huge invisible halo of dark matter. Think about that for a second. One cluster, in one direction of the sky, already outweighs entire swarms of ordinary galaxies around us. Let me give you the clearest possible example. In your room, the heaviest object decides how things fall. On Earth, the planet wins. In this part of the universe, clusters like Norma play that role. Its mass is so large that nearby galaxies, including ours, feel a tiny extra pull in that direction, layered on top of all the other motions we already have. You don't feel it. There's no wind of space on your face. And yet, on the scale of hundreds of millions of light years, our whole region is sliding very gently down that slope. But the Great Attractor isn't a single object. It's not one neat, glowing ball we can point to and say, "There, that's it." It's more like a tangle of heavy knots in a rope. Norma is one of the biggest knots, but around it you find neighboring clusters, long filaments of galaxies and sheets of matter all stitched together. Each one adds a little more weight, a little more curve to the landscape of space. Astronomers turn to X-ray light to see how deep these knots really are. When we look at Norma and its friends in X-rays, we see vast clouds of hot gas, tens of millions of degrees, filling the space between galaxies. Gas only gets that hot when it falls into a very deep gravitational well and slams into itself. That glow is a backlit sign saying, there is a lot of dark matter here. Here's something that will make you smile. Invisible light, the zone of avoidance, tries to hide this mass from us. In X-rays, it's almost like the universe left us a cheat code. And yet, even when we add up Norma, its neighboring clusters, and the surrounding filaments, the numbers don't quite close the case. Our motion, that 600 plus kilometers per second drift through the cosmic background, still points beyond them. I want you to hold that picture of a heavy knot in a rope, and then imagine the rope itself being pulled by something even larger, farther away. In the next part of this long, calm journey, we'll follow that pull out past the Great Attractor, into the truly giant structures that may be steering our entire corner of the universe. So hold that image of the rope in your mind. A heavy knot where the Great Attractor sits, and our whole Milky Way threaded through it. Now imagine that as we zoom out, we notice something unsettling. The rope isn't just pulled by that knot. The entire rope is bending toward an even larger weight, far off in the darkness. Gravity gets weaker with distance. You know this in your bones, even if you've never written an equation for it. A pen falls hard to your floor, but it doesn't leap toward the moon. The pull fades as you move away. And yet, on cosmic scales, sheer size can shout across incredible gaps of space. Think about that for a second. Let me give you the clearest possible example. Picture a paperclip on a table. You bring a small fridge magnet right up close, and the clip jumps. Now, slide that little magnet to the other side of the room. Nothing happens. But if you had a magnet the size of a car or a house, even across the room, you might still feel that tug. Distance matters. Strength matters too. Shapley is that house-sized magnet. It's a distant supercluster, hundreds of millions of light years away, packed with galaxy clusters, each one holding thousands of galaxies like the Milky Way. It sits far beyond the Great Attractor. And yet its combined mass is so huge that when astronomers model how galaxies flow through space, Shapley shows up not as a background detail, but as one of the main characters. When they trace the motion of thousands of galaxies, like tiny leaves drifting on a slow, invisible river, many of those flow lines don't just bend toward the Great Attractor. They keep curving, arcing toward Shapley's direction, as if the riverbed itself slopes that way. Some models even suggest Shapley's total mass might rival or exceed the entire region we first labeled the Great Attractor. Here's something that will make you smile. We named the Great Attractor before we realized there might be something even bossier sitting behind it. Our motion through the universe is not a single clean arrow. It's a sum of pushes and pulls. Nearby voids, those vast underdense regions, act like low spots in a mattress, letting us slide away. Local clusters and groups pull on us more directly. And then, layered on top, structures like Shapley stretch their long-range gravity across the cosmic room, shaping the overall flow of our entire supercluster. I want you to picture all of that as a map of currents, bright threads of motion weaving through darkness. We can follow those threads out to Shapley with some confidence. But beyond that, the map blurs. The data thin out. The light runs out. And yet the flow of galaxies keeps going. What else is out there, tugging on us from even deeper in the dark? What if the thing tugging on our entire galaxy is mostly made of something we can't see at all? You feel none of it in your chair or in the quiet of your room. And yet the Milky Way is surfing on a hidden tide of gravity right now. When we look at clusters and superclusters, we can weigh them two ways. We can count the light from stars and gas, and we can measure how fast galaxies orbit inside them. Those two answers don't match. The motions say there's far more mass than the light can account for. Most of the weight of these giant structures is dark matter, an invisible scaffold that only shows up through its pull. Think about that for a second. Now imagine taking that flow map from before, all those arrows of motion converging on the Great Attractor, and stretching out toward Shapley. On the screen, you see galaxies, little dots of light. But what you're really seeing is the shadow of something else. Those paths are like contour lines drawn over a landscape of dark matter. The galaxies are just tracing the hills and valleys of an unseen terrain. Let me give you the clearest possible example. I want you to picture a still, dusty room with a shaft of sunlight coming in through a window. At first, it looks empty. Then your eyes adjust, and you notice tiny motes of dust drifting and swirling. You can't see the air itself, but you can see what the air is doing. The dust is just along for the ride. In the universe, galaxies are those dust motes. Dark matter is the invisible air, full of slow, vast currents, pushing them around. Here's something that will make you smile. In our computers, we can actually turn the lights off on normal matter and run the universe with almost only dark matter. No stars, no glowing gas, just particles that don't shine, pulling on each other. Out of that darkness, a familiar picture emerges. Long filaments, dense knots, empty voids, a cosmic web. The flows in those simulations look a lot like the flows we measure in real space. The Milky Way falls into a filament, the filament into a cluster, the cluster toward something like Shapley. And yet, if you ask, what is dark matter made of, really? We have to admit, we don't know. We see its fingerprint in galaxy rotation, in cluster motions, in these giant rivers of galaxies. We build whole maps of its gravity, but not of its substance. The thing dragging our galaxy is mostly made of a kind of matter we do not understand. This is going to be a long, calm journey. In the next step, we'll zoom out again and see how all of this hidden structure turns our local patch of universe into just one tiny eddy in a much larger cosmic river. We build whole maps of its gravity, but not of its substance. And that sounds almost impossible at first. How do you draw a map of something you can't see, can't touch, and can't scoop into a jar on a lab bench? Here's something that will make you smile. Astronomers are basically cartographers of an invisible landscape. Instead of hills and valleys of rock and dirt, we map hills and valleys of gravity. We don't watch the land itself. We watch how things move across it. Every galaxy's path is a clue, a tiny pencil mark on a cosmic survey chart. Now imagine you and I are very small ants standing on a dark trampoline in a quiet room. The fabric is almost invisible. We can't see who is standing on it, or even if anyone is there at all. But we can feel the slopes under our feet. We can watch how loose marbles roll across the surface. Let me give you the clearest possible example. If all the marbles slowly drift toward one spot, we'd guess something heavy is standing there. We wouldn't see the person, only the way the fabric dips. That's exactly what we do with galaxies. We measure the slow, extra motions of thousands of them on top of the general expansion of space, and we watch where they seem to roll. Think about that for a second. By timing tiny shifts in light from distant galaxies, we reconstruct where the gravitational low points are, even when the mass making those dips stays hidden in the darkness. Here's something that will make you smile again. When astronomers did this for our cosmic neighborhood, they realized our Milky Way is just one marble on a vast trampoline called Laniakea, a supercluster about 500 million light-years across. On this invisible surface flow lines of galaxies, curve and stream, all draining toward a central basin. That basin is what we call the Great Attractor. We didn't name it because we're dramatic. We named it because whole swarms of galaxies are literally sliding its way. And farther out, beyond that dip, the fabric keeps on curving. An even more massive region, the Shapley supercluster, shows up as another deep hollow in this unseen terrain, tugging on Laniakea itself. We only know Shapley is there because galaxy clusters lean in its direction, like ants feeling a pull toward the edge of their world. I want you to picture those ants one more time, standing near the rim of their trampoline, feeling the fabric tilt downward into the darkness beyond. Wouldn't they suspect there's more out there, past what they can see or walk across? That's where we are now, tracing these graceful rivers of galaxies and quietly wondering what even larger structures might be waiting just beyond the edge of our current cosmic map. So if Shapley and the Great Attractor are these huge dimples in the cosmic trampoline, you might be tempted to relax and say, okay, mystery solved. Big clusters pull on us. We fall toward them. Story over. But when astronomers add up all the motion of our local group, of Laniakea, of other nearby rivers of galaxies, something still feels slightly off. You don't feel it. There's no wind in your room, no extra tug on your chair. And yet, when we measure our motion against the faint afterglow of the Big Bang, the Milky Way is racing at over 600 kilometers per second. Shapley and its neighbors explain a lot of that speed, especially once you include the dark matter we can't see. But some studies hint that the flow might keep going, like a river that doesn't quite slow down where you expect. Now imagine you're looking at a map of those flows. Little arrows for thousands of galaxies, all streaming along invisible slopes in space. Some arrows dive toward heavy superclusters, but others seem to be sliding away from a different kind of feature. Not a mountain of matter, but a valley of almost nothing. Think about that for a second. This is where a quietly strange idea comes in. The Dipole Repeller. It's not a sci-fi ray gun. It's more like a cosmic low-pressure zone. A vast region with less matter than average, tugging less than its surroundings, so everything around it ends up moving away. Let me give you the clearest possible example. Imagine a crowd in a room. If everyone rushes toward a singer on stage, that's like a great attractor. But if there's an empty patch where nobody wants to stand, the crowd thins out there, and people seem to be pushed away, even though nothing is shoving them. In space, those underdense regions can act as gentle repellers, complementing the pulls of Shapley, the Great Attractor, and other massive structures. The strange part is that we're trying to map all of this while sitting inside a very dusty, glowing galaxy. Our own Milky Way blocks a big strip of the sky with gas and stars, like a bright band of light smeared across the lens of our telescope. Add to that the simple fact that light takes time to travel. We only see out as far as the universe's age allows, and the farther we look, the fainter and redder everything becomes. Our maps fade into darkness long before the universe runs out of structure. So we're left asking, beyond Shapley, could there be even larger superclusters or giant walls of galaxies, quietly redirecting the paths of entire cosmic cities of stars? I want you to hold that idea. Enormous, unseen architecture, just past the edge of our current picture, already shaping where we go. Because whether the next big feature is a deeper attractor, a broader repeller, or something we haven't even named yet, we're already moving toward it, or away from it, carried along without our consent, and without any clear idea of what exactly is waiting out there in the dark, and without any clear idea of what exactly is waiting out there in the dark. Now jump cut. I want you to forget the galaxy for a moment and just come back to your room. The walls, the ceiling, the chair you're in, or the bed, or that spot on the couch you've slowly molded into your shape. Maybe there's the soft hum of a fan, the distant hiss of traffic, the tiny click of pipes or electronics. The glow of this screen is probably the brightest light in the room. Feel your body for a second. Your back against the chair. Your weight pressing into the mattress or the seat. Your feet on the floor, or tucked up under you, in whatever slightly awkward position you've decided is comfortable. Everything feels still, solid, unmoving. You don't feel a slide. You don't feel a pull. There's no sense that the Milky Way is rushing anywhere at all. And yet, as you sit here, all those things we just talked about, Laniakea, the Great Attractor, the Shapley supercluster, are tugging on you. Not in some poetic way, in a very literal, physical way. Think about that for a second. You are a warm, breathing patch of chemistry, a tiny pattern of living matter, inside a small, lit rectangle of space, being carried at hundreds of kilometers per second through a cosmic web you will never see with your own eyes. You didn't sign up for this ride. You didn't buy a ticket. And yet you're strapped in. Let me give you the clearest possible example. If we could suddenly switch your vision so you could see motion instead of color, your room would vanish. The walls, the bed, the fan, all of it would melt into one move-in frame, gliding along together. You'd see the Earth spinning, the Earth orbiting the Sun orbiting the center of the Milky Way, and the whole galaxy itself drifting, like a leaf on a slow, deep river of other galaxies. Here's something that will make you smile. From the universe's point of view, you are currently lying completely still. while doing something like 600 kilometers every second relative to the afterglow of the Big Bang. This is the calmest, high-speed journey you will ever take. Now imagine pressing pause on the cosmic map, but not in your room. In this video, we're going to zoom back out again in a moment and talk about how we measure these motions, how we know which way the Milky Way is sliding, and how we turn tiny shifts of light into a picture of invisible structure. This is going to be a long, calm journey. Big cosmic ideas, surprisingly down to earth. So stay in that chair, stay in that bed, feel how still you seem, and keep in the back of your mind that nothing about you is truly at rest. Because next, we're going to take that quiet, ordinary room and plug it into the moving map of the entire universe. So let's actually do it. Let's take that quiet, ordinary room and hang it inside a moving three-dimensional map of the universe. Right now, as you sit there, the Milky Way is not just spinning. It's sliding through space, being tugged by distant structures we can't see with our eyes. How do we even begin to chart that kind of invisible motion? We start with color, or more precisely, with how color stretches. When a galaxy is carried away from us by the expansion of the universe, its light is pulled to longer, redder wavelengths. Astronomers call this redshift. Think about that for a second. The space between you and another galaxy grows, and the light itself arrives changed, like a musical note played lower and lower as the source drifts away. By measuring that redshift, we can estimate how fast a galaxy is receding. Small shift, small speed. Big shift, big speed. Then, using a cosmological model, our best large-scale picture of how the universe expands, we turn that speed into an approximate distance. It's a bit like hearing a siren and guessing how far the ambulance is, just from how stretched the sound feels. But approximate isn't good enough when you're trying to see what is dragging an entire galaxy cluster. We need anchors. Let me give you the clearest possible example. Some stars, called Cepheid variables, pulse in brightness in a very regular way. The time they take to brighten and dim tells us their true power. Compare that true power to how bright they look, and you get distance. No ruler, just light. Type 1. A supernovae do something similar on a grander stage. These exploding stars reach almost the same peak brightness each time, like cosmic light bulbs set to a standard wattage. Spot one in a distant galaxy, measure how bright it appears, and you can mark how far away that galaxy really is. These are our standard candles, tiny points of light that quietly calibrate the whole universe. Now imagine the sky as a dark dome over your room. For each galaxy, we know its position on that dome, its direction, and, from redshift and standard candles, its distance. Put those together, and suddenly we can place that galaxy in 3D space, like sticking a pin into a vast, invisible foam ball. Do this not for 10 galaxies, but for thousands, then hundreds of thousands. Here's something that will make you smile. When we draw arrows showing how those galaxies move, patterns appear. Flows, streams, whole regions where galaxies, including our Milky Way, drift toward the same distant basin. Only with these slow, careful 3D maps can we see the giant currents of the cosmic ocean and start to trace what, out there in the darkness, is pulling all of us in. I want you to hold that picture, because next we're going to follow those flow lines to the place astronomers ominously named the Great Attractor. We've traced those flow lines on a map. Now imagine pressing play. Instead of still arrows on a page, you watch thousands of tiny galaxies begin to move, like glowing leaves drifting along invisible currents in the darkness. They stream toward the Great Attractor, past it toward Shapley, and even beyond. It feels less like a picture and more like weather. How do we know if that cosmic weather report is right? We do something both simple and wild. We build the universe in a computer, then watch it grow. Cosmologists start with a young universe, just after the Big Bang, when everything was almost perfectly smooth, with only tiny ripples in density. They feed that into a simulation, turn on gravity and expansion, and let it run for billions of years of virtual time. Think about that for a second. On your screen, in your room, an entire universe ages. Let me give you the clearest possible example. Imagine a huge dark cube filled with billions of points. Each point is a clump of matter. At first, they're nearly evenly spread. As the code steps forward, some regions pull a little harder, gather more mass, and grow into bright strands and nodes. Voids open up like black rooms between them. In the end, you see something familiar, a cosmic web that looks astonishingly like what our telescopes reveal. The trick is in the knobs we turn before we press play. How much dark matter do we put in? How much dark energy, the thing that makes space itself expand faster and faster? By adjusting those amounts, researchers can grow many virtual universes and pick the ones where the web of light most closely matches the one we actually see when we map the galaxies around the Milky Way. And then it gets more personal. Some simulations are not just random universes, they're tailored to our neighborhood. We ask the computer to grow a local group that looks like ours, with a Milky Way and Andromeda analog. A Virgo cluster in roughly the right place. A dense region like the Great Attractor. A massive Shapley-like concentration even farther out. Now imagine flying through that simulated space, tracing the same flow lines we measure in the real sky. When the simulated galaxies fall and swirl in almost the same way our real galaxies do, it's a quiet confirmation that our picture of what's dragging us is on the right track. And when the flows don't match, that's a clue that we've missed some mass or misjudged the pull of dark energy. Here's something that will make you smile. To test if our motion is special, we run many universes and discover we're not special at all. Our galaxy's 600 km/s plunge is not a random lurch. It's one thread in a vast, coherent pattern written into those first tiny ripples after the Big Bang. This is going to be a long, calm journey. Because next, we're going to step inside that pattern and visit the Great Attractor itself. Before we rush toward the Great Attractor, we need to pause and pick up a rule we've been quietly using all along. To understand why you're moving, you have to keep the structure in mind. Galaxy, group, supercluster, web. Miss one layer, and the story of your motion stops making sense. I want you to look around the room again. The walls, the ceiling, maybe a soft pool of light from a screen. You know you live in a building, on a street, inside a city, in a country. Each of those layers has its own traffic patterns. Morning elevators, busy intersections, rush hour ring roads, slow cargo ships crossing oceans. Your daily commute is really the sum of all those flows stacked together. Now imagine your cosmic commute. Start small. Inside the Milky Way, you orbit the galactic center along with the Sun, racing around the disk at about 230 kilometers per second. The stars around you are doing something similar, like cars on the same circular highway. Above and below that thin disk, a faint halo of stars and dark matter wraps around everything, shaping the gravity that keeps this whole rotating city of light from flying apart. Think about that for a second. Step up one layer. The Milky Way is not driving alone. It's part of the local group, a tiny neighborhood of a few dozen galaxies. We and Andromeda pull on each other. Smaller galaxies weave between us, and the whole group has its own slow, drifting dance. This is like your street and nearby streets, where local traffic patterns, one-way lanes, roundabouts, that one annoying speed bump, decide how you actually move from your apartment to the main road. One more step. Our local group lives inside the Laniakea supercluster, a sprawling basin of roughly 100,000 galaxies, about 500 million light-years across. Let me give you the clearest possible example. Picture a map of a huge city district seen from above, with rivers, highways, and side roads all funneling cars toward a central downtown. Laniakea is that district. Each galaxy is a tiny moving dot flowing along invisible gravitational roads toward shared low points in the landscape. And beyond even that, everything we've talked about is just one thread in the cosmic web. A vast network of filaments and voids, where superclusters line up like bright city chains separated by enormous, dark countryside. The web has its own traffic, too. Whole clusters slide along filaments, pulled by even larger concentrations of mass we can't fully see yet. Here's something that will make you smile. Your actual motion is the sum of all of this. Your orbit inside the Milky Way, the local group's drift, Laniakea's rivers of galaxies, and the web-level pools of structures like the Great Attractor and beyond. You didn't sign up for any of these commutes, and yet you're on all of them, every second. This is going to be a long, calm journey, because once we've mapped the structure and the motion, a quieter question appears. What does it mean, personally, to be a tiny passenger on these enormous layered currents of space and time? So let's zoom out from your seat on this layered commute and look at what the trip itself is telling us. Our whole local group is drifting at over 600 kilometers every second relative to the soft glow of the cosmic microwave background, that baby picture light from when the universe was young. Think about that for a second. If the universe were perfectly smooth on the largest scales, there'd be nothing to prefer one direction over another. No extra tug, no great downhill. But there is a downhill. That motion means space is lumpy, even across hundreds of millions of light years. Clusters, superclusters, and long strands of the cosmic web are tilting the playing field. We see nearby galaxies sharing the same slow fall, their paths bending toward the Great Attractor region, and beyond that toward the even heavier Shapley supercluster. You, your room, the Milky Way itself, are all part of that same invisible flow. Let me give you the clearest possible example. Astronomers can map galaxies around us and draw tiny arrows showing which way each one is drifting after you subtract the general expansion of the universe. Those arrows don't point randomly. They stream along filaments, converging into basins like rainwater running down the roof of a cosmic house. Most of the mass guiding that rain is dark matter, unseen but unmistakable in its pull. We don't just guess that dark matter is there because it's a trendy idea. We infer it because the visible galaxies alone don't have enough gravity to explain these speeds and directions. The flows of galaxies through the darkness act like tracer dye in a river, revealing the shape of the riverbed. By matching these motions to simulations, we can weigh how much normal matter there is and how much extra invisible matter must be wrapped around it. Now imagine using our galaxy's journey as a measuring tool. If you know how fast we're moving relative to the ancient background light, and you map how other galaxies move, you can start tuning the basic settings of the universe. How dense matter is, how strong dark energy is, how quickly structure could have grown from tiny ripples in the early light. When those numbers line up, it means our picture is on the right track. Here's something that will make you smile. The same alignment that makes your hairdryer work in your bathroom, following wires hidden in the walls, shows up on a cosmic scale. Our motion lines up with the threads of the cosmic web, just as you'd expect if those threads slowly grew from minuscule bumps in the newborn universe. It's a kind of quiet victory. The story we tell about structure forming from tiny seeds actually matches the way whole galaxies now drift. So your galaxy's journey isn't just a fun fact about speed. It's one of the main clues we have for how the universe is built and how it has changed over billions of years. In the next part, we'll turn that around and ask something more personal. If the cosmos is using us as a measuring stick, what does that say about our place inside it? And how should that shape the way you think about your own tiny stretch of time and space? If the cosmos is using us as a measuring stick, we should probably pause and actually feel what that stick is attached to. I want you to take a slow breath again. Let the air come in and go out without forcing it. Notice the simple sensation of sitting or lying still. The weight of your body, the contact with the chair, the bed, the floor. Look around the room, or just picture it with your eyes closed. The ceiling, maybe a soft glow of light, or the familiar darkness behind your eyelids. In this tiny bubble, you feel motionless, safe, quiet. Think about that for a second. Your inner world says, I'm not going anywhere. But underneath that stillness, the stack of motion is still there. The Earth is spinning, turning you around once every 24 hours. Our planet is looping around the sun at about 30 kilometers every second. The sun is carrying you on a much bigger path, orbiting the center of the Milky Way at hundreds of kilometers per second. And the whole galaxy, this giant river of starlight, is drifting toward distant attractors at over 600 kilometers per second. Now imagine all of that as a set of transparent arrows passing through your body. One arrow for the spin of Earth circling under you. One arrow for our orbit around the sun, sweeping you along a broad curve. Another for the sun's path around the galaxy, stretched across the darkness like a glowing hoop. And a final, even longer arrow pointing toward that mysterious region we call the Great Attractor and beyond. You don't feel any of them. No wind, no shaking, just the quiet pull of gravity doing its work. Let me give you the clearest possible example. If you dropped a pen right now, it would fall straight to the floor in your room. But in the time it takes to hit the ground, that pen has also moved hundreds of meters through space with Earth's spin, thousands with our orbit, and even more with the Milky Way's drift. A simple drop, drawn on top of all those invisible paths. Here's something that will make you smile. Your biggest worries today, the messages you haven't answered, the dishes in the sink, are all playing out on a tiny raft of rock and air, drifting through an unimaginably vast ocean of galaxies. And yet that idea can be strangely grounding. The more motion you stack under your feet, the more you see that your life is part of a much larger flow, not separate from it. This is going to be a long, calm journey, but we're nearing the last bend. In the final stretch, we'll zoom out one more time, watch those arrows merge into the larger currents of the universe, and then bring everything back down to something you can carry into tomorrow. What changes when you wake up knowing exactly what you're moving through? So let's actually ride that last bend together. I want you to look around the room you're in. The walls, the ceiling, maybe the quiet glow of a screen. This is your whole world most days. Your desk, your bed, a window, a door. Now imagine something impossible. You start to rise, slowly at first, like a very calm elevator that forgot to stop at the roof. You drift up through the ceiling, past pipes and insulation, into the cool night air above your street. You see your city as a patchwork of light, roads like bright veins, tiny cars sliding along. Keep going. Clouds slide past. The air thins. The blue fades. In a minute or two, the entire Earth is a round, shining marble beneath you. White swirls and dark oceans turning in silence. Think about that for a second. You don't stop. The moon's orbit shrinks into a pale ring. The distance that once felt enormous now looks like a small, careful circle drawn around your planet. Mars, Jupiter, Saturn fall into view, their paths wrapping the sun in nested ovals of light. The familiar solar system poster from school? It's now a tiny model floating in the dark, and you're already too far away to read the labels. You keep rising. The sun becomes just another star, then a faint dot lost in a glowing band. Let me give you the clearest possible example of scale. That hazy river across the sky, the Milky Way, is now a full disk in front of you. A flat whirlpool of hundreds of billions of stars. You can see the thinness of the disk, the bright center, the dimmer outskirts. Somewhere in a quiet suburb of one spiral arm, your entire life is hidden inside one unremarkable pixel. Pull back more. The Milky Way is no longer alone. It's one galaxy in a small neighborhood, the local group, sprinkled with companions like Andromeda, and dozens of smaller smudges. Each is a city of stars. Each has its own orbits, its own quiet rooms. Now imagine all those galaxies turning into dots. The view shifts again. A vast, hazy cloud appears. Laniakea, our home supercluster, about 500 million light-years across. Flow lines curve through this cloud like streams on a map, showing how galaxies drift along invisible slopes of gravity toward a broad basin, the region we call the Great Attractor, and beyond it, farther still, the even heavier Shapley concentration tugging on everything. Here's something that will make you smile. Your entire Milky Way is just one arrow in that cosmic traffic diagram. We zoom out one last time. The dots of Laniakea fade into a filament of the cosmic web, a bright thread crossing others in a vast three-dimensional lace of light and darkness. Superclusters sit at the knots. Long, thin bridges connect them over unbelievable distances. And Laniakea? It's just one crossing among countless others. Pause here. Hold this picture. Somewhere in that web, on a tiny planet, in a quiet suburb of a single galaxy, you are watching this video. How does it feel to know your exact address in a structure this large? What do you do with that feeling when the video ends? That feeling you have right now, that mix of awe and slight vertigo, is completely earned. A moment ago we were talking about hundreds of millions of light years, rivers of galaxies, invisible dark matter shaping everything. And you? You are a soft, fragile body in a room on a planet that could fit inside the Milky Way's disk billions of times over. Think about that for a second. Your entire life fits inside a thin layer of air clinging to a rock that orbits an average star in a quiet suburb of a single galaxy, which itself is just one faint thread in Laniakea's flow. If the universe were a vast forest, you wouldn't even be a leaf. You'd be closer to a cell on the skin of an ant walking on that leaf. And yet, here's the paradox. The Great Attractor cannot look back at itself. Laniakea cannot pause and say, "Ah, so this is the shape of my motion." Those enormous structures just move dumbly, silently, through darkness. But you, with your tiny brain and your tired eyes, can map them, name them, trace their paths with clear lines on a picture. Let me give you the clearest possible example. Right now, your whole galaxy is drifting at over 600 kilometers per second, relative to the faint afterglow of the Big Bang. The Milky Way doesn't know that. It just falls. But some primates on one of its planets built radio dishes, cooled detectors, wrote code, argued in rooms with whiteboards, and finally said, "We are moving this way, toward that mysterious region." That knowledge exists only in minds like yours. Now imagine the universe as a person slowly waking up. For almost all of cosmic history, there was no one to ask, "Where are we going?" Stars burned, clusters formed, superclusters tugged on each other in a slow dance. But there was no questioner. In a very quiet sense, when you understand the Great Attractor and Laniakea, the universe is becoming aware of its own large-scale motion through you. Here's something that will make you smile. This grand, poetic idea does not fix your inbox. It doesn't pay rent, solve an argument, or magically remove the ache in your back. The dishes in your sink do not care about dark matter. But knowing this can gently resize those problems. They are still real. They just no longer fill the entire sky. I want you to practice a kind of double vision. On one layer, the immediacy of your life, the light of your screen, the sound in your room, the next small decision you have to make. On another, a slow, almost silent background. Your galaxy, sliding along a cosmic web, pulled by structures you will never see directly. Pattern interrupt. Imagine pausing this video. The room goes quiet. Nothing obvious changes. And yet, while you make a cup of tea, the Milky Way keeps falling. The flow lines of Laniakea keep stretching. The Great Attractor keeps tugging. When you come back, your entire address in the universe will have shifted a tiny, measurable amount. In the next part, we'll bring this motion even closer, back down from superclusters to your own body, and ask a simple question. What does it actually feel like to live as a moving speck in a drifting galaxy? So before we zoom all the way back down into your body again, let me give you the clearest possible example of what we've actually done together so far. Right now, wherever you are, in a bright office or a dim bedroom, you feel still. No wind, no shaking, just you and the room. But that calm is an illusion painted over a lot of motion. We started in that darkness. We turned off the light, listened to the quiet, and noticed that even in perfect stillness, you're riding 3 huge motions at once. The Earth spinning and circling the Sun orbiting the center of the Milky Way, and the Milky Way itself sliding through space, carried along by something much larger than our single galaxy. Think about that for a second. To make sense of that, we climbed a kind of structural ladder. First, the Milky Way, our thin disk of stars, a tiny glowing street in a much bigger cosmic city. Then our local group, a small neighborhood of galaxies bound together. Above that, the Laniakea supercluster, this enormous region where tens of thousands of galaxies flow like slow traffic toward shared gravitational basins. Beyond Laniakea, we met the Great Attractor region, a patch of sky that bends the paths of entire clusters. Behind that, the even more massive Shapley supercluster, like a distant mountain range tugging on us from far away. And wrapped around all of it, we sketched the cosmic web itself, a vast 3-dimensional pattern of filaments and voids, where galaxies are just bright dust on invisible threads. We learned that our whole local group is moving at roughly 600 kilometers per second relative to the cosmic microwave background, that faint afterglow of the Big Bang that fills all of space. You don't feel 600 kilometers per second in your chair, but on the largest scales, that speed shows up as a tiny temperature tilt in that ancient light, revealing that something is dragging us. What is doing the dragging? Mostly mass we cannot see directly. Dark matter and the cosmic web form an invisible scaffold, a hidden framework of gravity. Galaxies like ours fall along its filaments into deep wells of mass, gathering in basins like the Great Attractor and Shapley, the way rainwater runs into lakes and then into oceans. Here's something that will make you smile. For all the complex maps, surveys, and velocity fields, the core picture is beautifully simple. We are leaves on a river. The river is space-time shaped by gravity and time. We drift where the current flows. Now imagine zooming back into that quiet room, into your own body, holding that whole ladder in your mind. In the next part, we'll ask, what does it mean, day to day, to be a tiny moving leaf in this vast, slow, cosmic river? So let's give that tiny moving leaf, you, a few simple sentences you can actually carry out of this room. Think about that for a second. We've just climbed this huge ladder of scales, but tomorrow you might just be standing in a kitchen or at a bus stop, trying to explain why our whole galaxy is being dragged through space. Let me give you the clearest possible example. If someone asks, what is this Great Attractor thing? You don't need a map of the universe. You can just say, it's a region of space with a lot of galaxies and dark matter that our whole galaxy is slowly falling toward. That's it. A crowded, heavy patch of the cosmic river, and we're one of the leaves drifting that way. Now imagine they look at you like, okay, but where are we in all of that? You can smile and say, we live in something called Laniakea. It's our home supercluster, a huge region where galaxies, including the Milky Way, all flow toward the same gravitational basin. Picture a giant bowl carved into space-time, with tens of thousands of galaxies sliding down its sides. Here's something that will make you smile. If they ask, are we actually moving right now? You can answer, relative to the afterglow of the Big Bang, our galaxy is moving at over 600 kilometers per second toward this region. You don't feel it. Your room is quiet. The light on your screen is steady. And yet, every second, you and everything you know are being carried through that ancient glow. At some point, someone will ask the most honest question of all. What's doing the pulling? And this is where you can share one of the strangest, calmest truths in science. Most of the stuff pulling us is invisible. We only know it's there because of how it tugs on galaxies. We call it dark matter, but you don't have to say much more than this. The universe is full of hidden weight, and that hidden weight shapes the paths of galaxies. Pattern interrupt time. I want you to actually try this. Not as a test, not to sound smart, but as a way to make this vast, slow motion feel a little more familiar. Pick one idea. The Great Attractor, Laniakea, our 600 km per second glide, or the invisible mass doing the pulling, and explain it to one person tomorrow. In this video, we're going to keep zooming out, but your life is still lived in ordinary rooms, with ordinary conversations. Bridging those two is where the real wonder lives. In the next part, we'll ask an even quieter question. What does it do to your sense of meaning when you know your whole world is part of a much larger cosmic flow? So let's bring this all the way back to you again. Right now, wherever you are already inside this moving river of galaxies, watching from a chair, a bed, a train seat, a quiet room. You didn't buy a ticket. You didn't even get a window seat. And yet you're on the ride. When this video ends, I want you to do something very simple. If you can, step outside or at least stand by a window and look for any patch of night sky. It doesn't have to be dramatic. A narrow slice between apartment buildings, a triangle of darkness above a street lamp, even a single bright point that manages to cut through the glow. Think about that for a second. Every star you can see with your eyes alone is part of the Milky Way. Not one of them is outside our galaxy. You might only notice a handful, or a few dozen, or a few hundred on a really clear night, but they're all neighbors in the same thin disk we've been talking about. You are not looking out at some random wallpaper of light. You're looking along the streets of your own galactic city. Now imagine that whole disk, that huge spinning pancake of stars, quietly sliding through space because of distant structures you will never see directly. Even the calmest, steadiest-looking star in your sky is being pulled along by that larger flow. It looks perfectly still. It is not still at all. Here's something that will make you smile. The star you use to make a wish is already halfway through a slow, million-year drift around the galaxy, and it didn't bother to tell you. If you live somewhere too bright to see the Milky Way band, don't worry. Let me give you the clearest possible example. Look up anyway. even if all you get is a dull orange haze or a couple of stubborn stars. Picture a faint, milky river arcing overhead, running from one horizon to the other. That invisible band is the cross-section of the galaxy's disk, and you're inside it, like someone standing under the roof of a vast, dark stadium, only catching the glow from a few exit signs. The motion of all this is not a threat. It's not a storm we need to brace for. This flow has been carrying stars for billions of years, long before there were eyes here to notice, and it will keep going long after. Our whole history plays out on a tiny moving platform, and the platform glides on. So wherever you are, in deep countryside darkness or city light, on a balcony or just under a ceiling, remember this: you are already inside the galaxy, and the galaxy is already on its way. You don't have to do anything. Just look up, hold that picture in your mind, and let it quietly change the way your own small room feels. If that quiet shift in how your room feels has started, you're already doing the real work. You're letting the galaxy in. And out beyond the Milky Way's soft band of light, there is so much more structure and so much more darkness than we've had time to wander through here. We only skimmed the surface of dark matter, of how invisible mass sculpts those great rivers of galaxies. We only touched the idea of the cosmic web, where each galaxy is one tiny glowing node in a vast branching network. Think about that for a second. Every point of light you've ever seen in the sky is already sitting on one of those filaments, being pulled and guided by something we can't see directly at all. If you like this kind of slow, careful walk through the universe, I want you to know there's a lot deeper we can go. In this video, we're going to stop before we map every strand of that web, but we could spend a whole calm episode just tracing how astronomers map dark matter, or following the future of the local group as it falls inward and reshapes our piece of the sky. Now imagine future nights where we zoom out again, this time not just to Laniakea, but to the flows that carry entire clusters toward the Great Attractor, and even beyond, toward the Shapley supercluster. We can watch the arrows of motion, see how the Milky Way is drifting at over 600 kilometers per second through that invisible landscape, and ask what that says about the hidden mass around us. If that sounds like a journey you'd like to take, you can quietly subscribe or follow, so you don't have to remember where this particular room in the internet is. No alarms, no pressure, just a way to come back when the next long, calm journey into the dark shows up. Here's something that will make you smile. Down in the comments, there will be hundreds or thousands of other tiny observers, each with their own picture of the universe in their head. I'd love for you to add yours. Where did you used to think the edge of our cosmic neighborhood was? The solar system? The Milky Way? Did hearing about Laniakea or the Great Attractor move that edge farther out in your mind? If you know someone who might enjoy feeling both smaller and more connected at the same time, you can send this their way. It's like opening a window in their room without turning on any extra light. All of this is optional. Curiosity is the only ticket. If that quiet question in you is still growing, stay with it, because the thing that's pulling our entire galaxy through the darkness is about to come into much sharper focus. So let's go back to where we started. You, in a room. The walls, the ceiling, maybe a half-empty mug, the quiet glow of this screen floating in the darkness around it. At the beginning, it was just you and this little rectangle of light. Now imagine that same scene, but with everything we've talked about quietly humming underneath it. You don't feel it. The desk doesn't slide, the floor doesn't tilt, no alarm goes off, and yet, under that stillness, the Earth is spinning. The Earth is circling the Sun. The Sun is orbiting the Milky Way, and the Milky Way is being dragged through a vast supercluster, flowing along invisible lines of gravity. Think about that for a second. I want you to picture what happens when the mental lights come back on. You tap the screen, the video ends. The room is just a room again. The same posters, the same window, the same ceiling you might stare at when you can't sleep. But now there's a new, invisible backdrop behind all of it. A galaxy sliding at hundreds of kilometers per second through a web of stars and silence. Here's something that will make you smile. Tomorrow, you might be late for work, or stuck in traffic, or doing dishes you really don't want to do. You won't be thinking about dark matter, or the Great Attractor, or the Laniakea supercluster. And that's completely fine. The universe does not need your attention to keep moving. It will keep pulling, flowing, and orbiting whether you remember any of these names or not. Let me give you the clearest possible example. You don't have to think about your heart to keep it beating. You don't have to think about gravity to keep your feet on the floor. In the same quiet way, you don't have to think about our galaxy's motion to stay on this ride. You're strapped in by gravity at every scale. But every once in a while, when you step outside at night and the sky is clear, you might look up and feel a small, private echo of this idea. Those tiny points of light, that faint band of the Milky Way, are not just a backdrop. They are part of the giant ship you're riding, being gently dragged through the dark by something we can't fully see. So when this ends and you stand up, remember, wherever you go next, you're already on the journey. You are carried by a galaxy, flowing through a supercluster, drifting through a cosmic web that stretches far beyond any room you'll ever sit in. The lights can come back on. The day can be ordinary again. But behind every ordinary moment, you are moving with all of this, and that motion never stops.